My purpose is first to show some general ideas about quantum control and optimal control, explain our method for optimizing dynamics, showing applications to the experiment in the group of Jörg Schmidtmeyer that we did in the past, hinting at new developments which might be useful for some projects that we might develop here. And I also added some part for Spiros connecting to this question about what we call the speed limit, which manifests itself in this sort of very infinite long range and very interesting dynamics and Lieb-Robinson dynamics in the Sine-Gordon model, which we have analyzed until now in discrete models, and so this is also something that connects to your stuff. And there is also a connection to Simone's talk, because this is some activity that we have done in the context of the same European project in which, oh, good morning, in which we are dealing with quantum simulation with ultra-cold Rydberg atoms, okay? So the ideas of optimal control that I have here in the context of the present week are indeed related to how you can prepare states of ultra-cold atoms. Now, even though it is not polite, because normally you wouldn't address individual people in the audience, but since I tried to, we have a not very broad audience, may I ask you if you're a physicist or a mathematician? A mathematician, okay. Oh, okay, beautiful, okay. Just to say if, okay, just. So I will try, because I am trying to make the talk relevant for everyone here, because there is not many people, so I will try also to take that into account. Because indeed there are some mathematical aspects in what we are doing, which even though it's of course applied to controlling quantum dynamics, those are methods borrowed from mathematical physics. Typically, there is a theorem, as I like to say, always that, you know, for any problem in theoretical physics, there exists a Russian who solved it 40 years ago and published it in some obscure journal, and during your talk, a friend or relative of the Russian will stand up and say, we already solved it 40 years ago. So this is no exception. In fact, the name of the Russian here is Grotov, okay? And so this is really some ideas that we got from mathematical physics and we translated to quantum technologies and quantum mechanics. And so I will show some examples of that from the context of ultra-cold atoms in particular, which is what we did with Jörg Schmidtmeyer, but also in the context of NV centers, because there is, even though it is not relevant for quantum simulation, but this is the place in which we demonstrated a closed loop approach, which might be relevant for some of the discussions that we are having. So this is exactly this aspect of closing the control loop, not only locally, like in your lab, but possibly also over the cloud. In fact, the last experiment that I will show was done in the lab of Misha Lukin in Harvard, and we found out after, so we enabled access to our server for optimization, and we found out that they wrote another paper using our software without telling us. And now they submitted it to the archive, and this is great news. Okay, of course, they very correctly asked us whether we wanted to be involved, and we said, no, because our purpose here is really to have a tool which experimentalists can use without our PhD students standing in their lab, but really using as a service for optimizing experiments. So this is, we are even thinking of starting a startup in this direction. There is already a few startups around the world which are doing that. So, and then the last part is really with these Rydberg atoms, how we drive this to the limit, and we create the fattest Schrödinger cat that mankind has ever done, which is particularly relevant in the Boltzmann gas, okay, because we are just steps away from his very holy and sacred desk, which I think is in Marcus Aspelmeyer's office, I think still, right? I'm going to have lunch with Marcus today after the talk. So, the main idea of control is, well, I have a certain quantum system with certain discrete levels, and they depend on time. And let's say that I want to make a transition, which may be non-trivial, from maybe some ground state of the system to the ground state after crossing maybe a transition, like I want to prepare the ground state of some Manybody system. And so there is a, and why do I say after crossing a transition? Because here there is a little level crossing which, you know, hints at that. So the typical way in which one does this, you say, I am in a certain phase, I want to go to another phase, I can do it adiabatically, slowly. Okay, and this is something which, interestingly, is a very central concept in time-dependent quantum dynamics, but also in thermodynamics, but it has different meanings. And connecting those or not connecting them is really part of some of the discussions that we are having here. So an adiabatic strategy would be that I go slowly from the ground state on one side to the ground state on the other side, and then I stay more or less close to that. But then, of course, if I shrink the time because I have reasons, because maybe the experiment with some quantum systems can only survive for a certain time, I want to go fast. If I now use any arbitrary, let's say, time dependence for my parameters, then I will have, there is another Russian who is sitting here, his name is Landau, so this is the Landau-Zener crossing, and so, of course, you have a high energy and you do not hit the state that you want. So what does optimal control do? Optimal control is essentially exciting the system maybe more in the beginning, but then converging, doing it in a proper way so that you converge, then you are not in the ground state throughout the process, but just at the end when it is interesting for you. So this is the basic idea, and here is the way in which we developed almost 10 years ago to do this. So you start with a certain simple time dependence of your control parameter, okay? Which could be anything, the position of a trap if you want to transport some atoms from here to there. And then what you do is, here comes our chopped random basis algorithm, the CRAB algorithm. And the problem is that when I say this in German-speaking world, not all my colleagues tend to pronounce it like the CRAB algorithm, unfortunately. So, well, but we realized that after we published, it was too late. So now what this thing does is it takes a basis which is randomized in the sense that these functions here, could have, for instance, some frequency which has some random factor, some random component in there. And what you do is you reduce your problem to a sum over this basis. So your pulse, you update it based only on a few parameters. Because you chop the basis, you have a sum only which is a function of a few of these parameters. And what you get is you reduce your control problem to a landscape in a few dimensions. Let's say that we have 2 dimensions, so it is really a 2-dimensional landscape. And let's imagine that the initial pulse is giving me an error which is relatively high. So in this landscape, I'm over there. The error is not low as I would like it to be, for instance, here. So the question is, how can I get down? How can I reduce the error in a systematic way? And there are different methods for doing this minimization. The one which we used frequently, but it is not the only one, is just rolling down this little triangle through the landscape until you get a certain shape. The advantage here, regardless of the ways in which you do this minimization, this path can be also calculated with machine learning methods with a lot of different possibilities that we are exploring. The important point is, at the end, the pulse that I have has a shape which is given by maybe, for instance, just a few Fourier components. So it is not something which is unrealizable. I can tune it in such a way that in an experiment it can be done. And this does not require an analytical solution. I can use, as we were discussing earlier, any figure of merit, either calculated or measured in a closed loop configuration, in order to get this optimization. And I will show examples of that. So here are some first experiments with Openloop. It is what I call the plug and pray approach, in the sense that you plug your algorithm and then hopefully it will work, and sometimes it even does. So here is an example with a Manybody system, because I said before we want to manipulate a Manybody system. In this case, it is atoms in an optical lattice which are interact according to the Bose-Hubbard model, and we have already had some discussions of such models during the rest of the week. Typically, in the context of quantum simulation, this gets used in 2 ways. On one end, of course, it is a very central model for Manybody physics that you can simulate if you have an optical lattice and an array of atoms. On the other hand, if you want to do such quantum simulation, you want to prepare the state. So here we are focusing on preparing the state, starting with a Bose-Einstein condensate in my optical lattice, which is maybe low in depth. And then I want to raise the barrier in order to get to another phase, the multi-insulating phase, in which I have 1 atom per optical lattice side. And then typically it takes the best optimized already for about 10 years. For instance, in Manuel Bloch's lab, the best type of thing is, a few hundred, minimum 100 milliseconds. What we want to do is to go much lower than that. And if you go faster, the type of defects, the excitations that you have, is the higher energy states are states which are bad for your quantum register because you have maybe 2 atoms on one lattice site and 0 atoms in the nearby lattice site. And so this is something which you do not want to have. So you want to optimize your process in order to get, on a shorter time scale, a defect-free lattice. So this is what we did. So the yellow line is the pulse shape that they had after many years of really refining this technique, and the blue and red lines are our tries, our attempts to do it 1 order of magnitude faster. And then the red line is just a linear ramp, like raising linearly the depth of the barrier. And then the blue ramp is optimized. You see, it is not a completely funny shape, but somehow it is also something which does not have a simple sinusoidal shape. It is really coming from the physics of the system. This has been done in Openloop, like simulating with DMRG methods. Oh, this is very bad. That was not meant to happen. Okay, interesting. So, how do I do that? I probably go to some do not disturb thing, which should exist. Yes, beautiful. I am very sorry. It is just the problem is that I updated yesterday night the operating system on my cell phone, and apparently it is very smart, much smarter than I can possibly follow it. It never happened before. Okay. Yes. Beautiful. Yes. The open loop, I have, okay, so let me, oh yeah, that's right, so we have to. So let me go on to the, to a picture which explains that, okay. Just, it would be this picture, okay. So, open loop means I just have a simulation of my system, okay. So I calculate the evolution of my system. I have Grosspitaevsky dynamics, whatever, and numerically I say, okay, if I do a certain pulse with this shape, I will get a certain fidelity, let's say. And then my algorithm is iterating this. So it is indeed a loop, an iteration, which contains only a numerical simulation. Instead, I can also say, okay, now I want to test it on my system, and this is closed loop in the sense that the loop is closed onto the actual physical system, and then I try with my either optimized or guess pulse, which is maybe the result of some theoretical optimization or just my guess. I apply to the system, I measure the actual figure of merit, and then I go back. So the blue one is the closed loop involving the experiment, and the other one is open because, I calculate some function, and then I will apply to the experiment without feedback. So that's what we mean by that. And this is actually a very important and good question, because in the language of control theorists, there is always different views on that. So what we call closed loop, for instance, a really serious engineer would never call closed loop. Okay, but whatever. So, but we are not serious engineers, we are just boring physicists. So, so here we go, and this is what was calculated via our simulation and applied to the system. And when you apply it to the system, then you see that, so here you have the red line, and there is the calculated, and red is the measured density of defects. So what you would have to have is just, here is unity. You would have unit occupancy in the mid-region of the quantum register. It is a few tens of atoms, and you want to make sure that there is one per lattice site, and here's the density of defects, which is, oscillating by about 15%. And if you measure it, it would be flat if you do it with a yellow line, so with a diabatic line. But then if you now do the optimized one with the blue points, then essentially it is indistinguishable from the one which is a diabatic. Only it is 10 times faster. And really, you can show that you need the many-body dynamics. You need to excite those many-body states, otherwise this does not work. So this is an experiment that we did, because then once you do this, you can say, let's try to do it as fast as possible. This is what we call the quantum speed limit, and connects to the last part of the talk and our discussion we had the other day. So with Jörg Schmidmeier, we tried to do an experiment at the quantum speed limit, which was, in this case, excitation of a condensate from the ground to the first excited state, and we wanted to do it as fast as possible to excite and then de-excite in order to do some Ramsey measurement of some external field. Here are the pulse shapes which come out, and you see they depend on the number of atoms, because even though this is mean field, still, of course, the interaction has an impact on the dynamics in terms of what we were discussing also before, and so the shapes are quite different, and they are actually quite articulated. So one would say, okay, this is really very fine-tuning. How can we hope that it will work? Because this is still open loop. I calculate and I hope that it works. And so this is what is the result of the experiment. So here is the simulation. You can see really here, because time goes from top to bottom. Yeah, and you have the population, the density. So you have one hump in your wave function in the beginning, ground state, and two humps, which is first excited state at the end. And here you see that really you have some oscillation, which is really, bringing you outside of that subspace. And here is when they measure it, which in the beginning I thought it was the student which was tricking me, because I mean it's almost identical. It's actually equal to 99.something%, and this is not a problem with the projector. It's just subtracting. It washes away the features. And this is, of course, is telling you that Jörg is a fantastic experimentalist, and his team is a fantastic team. But it also somehow tells that the method works as well. Okay. So then, if you want to push it to the speed limit, this is relevant here, because here you have to do excitation and de-excitation. And interestingly, Jörg had already used optimization down to 5 milliseconds for the optimizing pulse, but then he didn't have time within the decoherence time to have, the de-excitation and do the full Ramsey sequence. But we calculated that theoretically that the speed limit would be around 1 millisecond. And so we optimized, and we got 1 millisecond, and here are the beautiful Ramsey fringes that you can obtain out of this to measure, in this case, some magnetic field. And so even in open loop, this is working, and it is working for condensates, which is exactly the discussion that we are having here. And well, now we would like to move towards closed loop. So to move towards closed loop, we better start with a simpler system in which we have things a little bit better under control. So in this sense, we go to NV centers, which have a different application in quantum technology, which is not quantum simulation, but rather quantum sensing, sorry. Why is this thing? Yes. And here is the Hamiltonian of this system, and it is controlled by it is a few-level system, which is controlled by an external field. And again, we use our Crab method in order to optimize that field. Here is, for instance, a picture of what you get if you take into account everything. So this is still open loop, but it takes into account the waveform generator that they have and the amplifier and all the electronics, which takes the signal that you want to put into the system and distorts it in some way, but you can take that into account, and you get some rotation. This would be a pi rotation on the Bloch sphere, which instead of going straight from north to south, takes some detour, which is exactly that allows you to massage the system back into place, like we had in the first example. So here is, for instance, a pi pulse, a pi half pulse, and the pulse that we calculated in order also to take into account what is the rise time, the time resolution, and everything in their experiment. And here is what they measure. So they do tomography of these rotated states, and they get a very high fidelity, which is what we predicted. And, well, so it means that this system can be controlled in a simple way. And now, as I said, we would like to go to a situation in which we can do it in a closed-loop situation. So how do we do that? I already explained the meaning of this transparency here, and now how does it look like if you try to do this in practice? Now, one question which very often you don't need even to be a mathematician, but even some physicists or a lot of physicists realize that, if you have this landscape, well, you can have local minima. Okay, so you can get stuck, you minimize, but the landscape can be very, very complex. And so what happens? You can get stuck in a local minimum, and then you optimize going down, down in the landscape, but you do not reach the full global minimum. So you have to do something about this, because if the system is going by itself, it has to self-calibrate, it must also have the ability itself to escape those minima. So here is a method that we developed. So here is an example, it's just a cartoon, if you wish, of more than one possible optimum in a landscape. And then what we do is we exploit this randomized part. I mentioned before that our crab pulse means that the frequencies of my Fourier components, for instance, have some random components. So in the frequency there is a random number which is changed, like shaking a little bit from iteration to iteration. So what we do is, when we detect that we are getting stuck in some local minimum because it is no longer going down, the optimization, we just throw away one of these frequencies and we abruptly change that in some random fashion. And so from what we had before, which was this iteration, this iterative process of finding the proper amplitudes, we go to what we call super iterations, which means that we start anew with a new set of frequencies, and actually we just need to drop one. And what does this do? What it does is it changes the landscape, because that landscape that I showed before, depends on, it's a landscape of the error as a function of the amplitudes. Amplitudes of what? Of certain Fourier components or certain basis functions. So if you change that, the shape of the landscape changes. And what turns out to be the case is that a landscape with a local minimum, in most cases, and you can demonstrate mathematically that this is really dense in the set of all possible configurations, the landscape opens up, and what you can do is you unlock the trap and your optimization can proceed further downhill. So this is now what we implemented in a closed loop. So here you see the loop, the sample of diamond with the structure which is here, which is sitting and driven by some laser pulse. Then there is a readout of the state, and then in a closed loop, you update the control using our, now it's called decrab, we call it dressed crab, in the sense that there is this additional layer that we put on it in order to overcome local minima. And in the end, your goal is to get something like this. So we try how it works. And in the beginning, well, we want to achieve a Hadamard gate. So let's say square root of a knot rotation. And we start with some random guess for the pulse shape. And then here's what happens. You see, here is not number of iterations, but hours, in the sense that in the experiment, every iteration, you're required to measure, to take the proper statistics, and so on and so forth. And so what matters is, it has to be efficient, okay? This is why we cannot afford to be stuck in local minima for long. This is why our decrab algorithm helps. And you see that, you come at night, fidelity is 50%, you come tomorrow morning, you switch it on, tomorrow morning the fidelity has reached 100% within the experimental error. You do the tomography, you see that this is really the gate that you wanted. And here is to show that, the standard pulse, the initial pulse, is this blue line. And again, the algorithm is doing something, is creating this black line. And again, it is not just a simple sinusoid, but it is something which is told you by the system. The system is telling you, this is what I can realize, and so it does work for it. So what we want to do is to be able, as I mentioned before, to operate this over an internet connection, between Jülich and Vienna, okay? It was between Jülich and Harvard for the thing that I will show afterwards. The first example of this remote decrab, which we call red crab, is essentially an experiment that was done in a context of, it's called citizen science. This is also interesting in itself. So there is a server in Aarhus. The website is called scienceathome.org. you can go there and play quantum control games with your mobile phone. There is even an app. And so real people, not physicists, okay, they are challenged to like transport an atom. There is a real-time simulation. You move a trap with your mouse, and there is a real-time simulation which shows you the wave function, and you get a prize if you get a high fidelity. And how do you get an intuition? Because there is this wave function which wobbles. It looks like a liquid, and then you want to transport it. And literally thousands of people played this hundreds of thousands of times. And so what we did was, and at some point, they do it via simulation, but also they did it with optimizing an experiment, okay? So the real creation of a BEC. And so on one day, there was this challenge which was announced. The experiment was accessible to the public. Everybody could play. And we competed against real people. And this may seem trivial because you say, how can people beat an automatic algorithm? But previous versions, so this Krotov algorithm that I mentioned before, the Russian which inspired us to start all of this, this was beaten by some of the humans in some of the simulated games, okay? Because when you try to do it fast, your landscape gets very, very complicated. You have a lot of local minima, and so you can get stuck. And sometimes humans with intuition, they say, oh, I should go there. It's funny to read the descriptions. They say, oh, you have to go there, but you have to wait because the atom is not sure what to do, and then you can help it, and it will go there. And so people develop some intuition, which is really intelligent, and then in some cases they could outperform the Krotov algorithm. So we were quite nervous, because if they outperform our crab algorithm, then it means that really my German colleagues have right. They are right, that this is really the crab algorithm. Okay, so let us see what happens. And fortunately, I can proudly announce that, and interestingly, not by much, okay, but interestingly, our red line, went above the best performance of the human players, okay, so which is good. What is even more interesting, I don't know if I have the slide here. No, I don't have the slide here, so let me just say it. What is even more interesting is that you can combine some of the solutions that the players, some of the paths in parameter space that the human players found, which have a certain characteristics, with some of the automatic calculated paths, and do hybrid optimization paths. And this, is something that we are still exploring, because using machine learning may be something that will allow us to discover new classes and to improve further. So this is the frontier that we are having now, not just using this simplex, this simple model for method for minimizing, but going towards more intelligent tools. That's the current research that we are having. Now, what we did is, after we demonstrated a sort of a byproduct of this was to demonstrate that our method worked over the cloud, in the sense that there is an API, a programmer interface which passes data, and then we have a server. There is a little program which we can give to them as a client to install there, and then it really works. So we wanted to test this with some more serious type of thing, and here is what we did. So, coming now to the point of the lattice, Rydberg lattice gas, in particular the experiment by Michel Lukin, but same experiment is, for instance, conducted here in Europe by Antoine Brevet, which is the coordinator of our project. He will be here next week, together with all the colleagues, for our workshop, to which everyone is invited. We have our annual workshop of our project on Rydberg atoms, so you are welcome to join the scientific talks. So, what they do is they can prepare first non-deterministically, and then with some noise removing process, like they take all the atoms which initially they are randomly distributed in this lattice, then they take them in a nice array in which they are one per site. And now what we want to do is what I had in my first transparency, which is to go, by changing in this case the detuning for some laser transition, from one state in which the atoms are all in the ground state to another state, which is they are in a superposition of down, up, down, up, down, up, plus up, down, up, down, up, down, which is a GHZ state. So we did the calculation and the closed loop optimization. Here is the result, okay? So this is a 20-qubit GHZ state, which is the largest JZ state that has been created. So there are also experiments from IBM and from a Chinese group with superconducting qubits, which arrive to 18 qubits. Of course, I mean, like here in Austria in particular, the group of Rainer Blatt can easily do probably more than that because they have a fully functioning quantum computer. But the nice thing for us is that, you know, the previous world record was, which actually in the meantime, I didn't update this, but it is published in Science last month. So here is the point. So if you, you know, do the optimal simulation, okay, you get there. If you do some analytical simulation, you see that, I mean, you are not able to, just with some simple method like I showed before, you are not able to cross the threshold of 50% fidelity. And then the experiment, I mean, 20 is the point in which we, using the optimized figure, we arrived still at more than 50% fidelity, and they are working on improved version of the apparatus to sort of to improve it further and to possibly get closer to the theoretical value. But this is really not only showing that it works, but that really this optimal control in a closed-loop approach enables you to achieve something which was utterly impossible to do before. So that's, I think, yes, that was my last slide of the experimental part. And now I have a couple slides which are for Spiros, because we had this discussion on speed limits. Actually, this is how we call it, not how they call it. So, and the point here is, what about the complexity? Because, you know, there is a very complex landscape, and I told you that all this many-body dynamics, which, you know, is even, you know, soon impossible to simulate with a classical computer, that you can control it with just a few parameters. So this does not seem very reasonable, okay? So we wanted to understand why it is that, in fact, if you look at the dependence of the error on the number of basis functions in your algorithm, on the bandwidth of the pulse, you see that it really decays exponentially. Actually, it's a exponential, the number to the square. It's a Gaussian. So I is the infidelity, the error in your final. So typically, so this is calculated for, you know, this transition in an Ising system. But typically, this is what we always find. If we need only a few of those Fourier components, 4, 5, because, you know, then you just go to convergence. And we never, I mean, for a long time, we could not understand why this was the case. So, but then, I mean, this was a collaboration we had with Seth Lloyd. And Seth is, you know, used to think big, like he wrote this book, Programming the Universe, and he wrote papers about what is the computational power of this piece of wood, okay? So what is the ultimate thing that you can do? And doing this, he used a very interesting perspective, which is from information theory, which in the end is what solved the trouble, so to say. So we look at the Hilbert space of our entire system. Hilbert space is a big place, exponentially large in the number of qubits or components. But the fact is that typically, even if you have many-body dynamics, there is a subspace of this Hilbert space which is relevant for your dynamics. This is actually the reason why you can do these tensor network simulations, these DMRG simulations, because, you know, for those systems, entanglement never goes too big. So there is a part of the Hilbert space which is relevant for your dynamics. And so if you look more in detail, you will see that, okay, there is the whole Hilbert space, which is very big. There is the dynamically relevant subspace, which is smaller than that. And our goal is to reach some state with our control procedure, which is this red part in here, okay? And we want to reach it with some accuracy. And now I don't know why this guy keeps going back. Sorry about that. The goal is to reach that particular state. So if we now quantify the resources that we need to do that, okay, the question is, I have a certain dimension for my subspace, and I have a certain accuracy in which I want to reach my state. And the point is I have to specify my state over all possibilities in that subspace, because I already know that my system will not go throughout the whole Hilbert space. So I have a certain number of qubits, certain number of bits, of classical bits, which I need to specify the goal state. I need to tell the system, go there. I have to define there what it is. And then I have a certain number of bits, which physically are the way in which I am talking to the system. I specify my control pulse. So how is this quantified? Well, to specify the goal state, in general, I will need, a number of bits which is equal to the logarithm, its bits, of the inverse dimension of this little red area over the yellow area. And that's the catch. It's not the whole dynamics, the whole dimension of the whole Hilbert space, but just the little part in which my dynamics is taking place. How many bits do I need to specify a certain pulse shape? Well, this is Shannon classical information theory. This is bandwidth times the total time times the bit depth that I use to define the accuracy that I have to define my pulse. So now, if I say I want to reach a certain accuracy, okay, I want my goal state within a certain error, then solving for that gives me already that there is an exponential behavior as a function of the number of Fourier components. And for a certain accuracy, the number of Fourier components is in some way proportional to the dimension of this space in which the dynamics is taking place. Can we check that? The statement here is the bandwidth of our optimal control scales like some property of the system, the complexity of the dynamics. So, for instance, if I have an integrable versus a non-integrable system, of course, those are classical concepts, but if I apply this to the quantum analogs, do I see a different behavior? In this case, we can take a simple model, because this is just a theoretical simulation, an Ising model, and then we put a component. There is the transverse field, but also some parallel component in the field. And if that component is 0, the system is integrable in the classical analog. And if it is non-zero, then it is non-integrable. So what we see is that if we look, so this B was the width of this exponential decay that we had before, a measure of how many components I need. This is, of course, for as much as you can simulate, which is just, with a few units, but it seems there is a strong indication that it diverges in the presence of a non-integrable system, and it does not diverge if the system has a classical analog which is integrable. So it seems that the width, the number of Fourier components, is indeed proportional to that dimension. And this is a first reflection. And actually, this I pulled from an older talk because I wanted really to connect to what we said the other day. Why is it connected? Because it's the question, how many resources, how complex is that? Can I drive a certain transition? Can I drive my system? In other words, can I propagate information across my system, in your case, quickly enough? What is the limit with which I can do that? And how many resources do I need to that for doing that? So what we get from here is, but it is only a conjecture, that essentially if I want to manipulate a many-body system globally, just with some pulse which is shaking things around, and I want to prepare some state, I want to, the information that I want to impose on the system to reach the whole size of the system, that this is something which has to do with its complexity, with the size of the relevant Hilbert space. What does this mean? It means that, and again, this is a conjecture, the reason why we don't have a much larger Schrödinger cat is not a static reason, because what we normally hear in quantum mechanics is you do not see macroscopic objects in superpositions because there is decoherence. Because if you would have that, then it would decay very quickly, you would not see it. And this is true, but it is only a if-then. It doesn't tell you whether it is at all possible to prepare at all a system in a macroscopically coherent state. And this fact of, and this is connected also to the Lieb-Robinson bound in the sense that it depends on, if I start shaking the system in some place, I need the information to propagate in the system. How fast is that? My point is that this, for a macroscopic system, is necessarily very slow. And if it really grows with the complexity of the system, then it means that we are never going to see a Schrödinger cat state because nobody, not even God, can prepare it. Not even in a world without the coherence. Because preparing a macroscopic Schrödinger cat state is impossible. The quantum speed limit for that is longer than the age of the universe. So it is really a dynamical reason why we do not have macroscopic quantum phenomena. And this is something which is preceding the fact that there may be decoherence, and if you would prepare it, then it would decay. So the question, this is why I'm very interested in these questions about, speed of information propagation. As I mentioned, this is just in discrete systems, so perhaps it would be kind of very, 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 fascinating to see what happens in your case. Here, for those who were not here, I'm connecting to a talk that was given, I think, on the second day of this week, and so I just wanted to build this connection because coming from this control aspect, this is why I think the dynamics is essential. And now I hope I have convinced those of you who were here of the reason why I was insisting that the trick is in how the time dependence during the quench, was so relevant. Because it has to do with, pulse shaping, it has to do with control, it has to do with what can be achieved within a certain finite time with certain resources. Okay, so this was maybe something which was a hint which was less relevant for those of you who were not here with us the whole week, but since we are having this sort of discussions and workshop, then I thought it might be relevant, and this brings me to my summary, which is simply that, it seems to be possible, indeed, to control quantum systems with the Crab method, not only few-body systems, but also complex many-body systems. It works in open and closed-loop scenarios, as we have defined before. It works also over the internet, and it allows you to create the fattest Schrödinger cat that mankind ever created. And this is it. And of course, I stand ready for questions. Or if they ask us to use the mic, like you have to kind of switch it on. Yes, because then they can record what you are saying.
So thank you for the talk, very nice, and even as a experimentalist, it was very understandable for us. So, so my first simple question is, what was the B again there? Was it the number of the Fourier components?
The B was the width of the, it was this sort of this width of this Gaussian. So, the half width of this curve somehow, which tells you an estimate of how many Fourier components are relevant there.
And so, related to this, do you always use Fourier bases?
No, not always, no. So in many cases, yes, but we have done, for instance, in this case of the experiment with Orhus, it was a multiple exponential, for instance, because that was just a ramp of ramping down the RF knife for making the BC. Okay, and so in that case, the natural basis function would be some double exponential. So it's not necessary. It's a method which works regardless of whether you are having Fourier components or others for a basis. So it depends what can be implemented and what is in your system that your system is reacting to. That's the important part.
And so for now about the experiment in Harvard, for each to prepare that, the control parameter was the detuning of every single site, the lasers on every single site?
No, it was global. It was global.
So it was a single control parameter?
Yes.
Okay.
And the reason is that, it goes, so if you look at the level scheme of this system, I think it is here. If you look at the level system, so the detuning is a global one, and the system undergoes several transitions between different configurations, and some of the excited states are not the ones that you want, and this one is the ground state after all these transitions. And again, the problem, so there is a path an adiabatic path which connects your initial state to the final state, but following it adiabatically would take way too long because those are Rydberg atoms, they decay, and so you wouldn't see anything. And so this is why you had to go to do this transition much faster, which connects back to our initial picture in which we wanted to do this many-body transition over a short time.
Thank you.
Sure. Any other questions?
Yeah, so you talked about a code. How can we access that code?
Oh, yes. So I think, I'm not sure, maybe Marie already has it, because when we came to Vienna, so we are, both Jörg's group and my group, we are in a Marie Curie project, which is called Cusco, and Tian is the student in your group, which is paid by that. So in my group, it's Fila Rembold. So when we came with Fila. Now Tian is going to visit us, and either they already have the client part, or Fila can give it, or, I mean, it is straightforward. It's possible that they already have it. So Marek seems to have a question.
So you were also mentioning the landscapes for optimization. Could you comment on the NISQ heuristics, like the VQE, what kind of landscapes you would expect there, and whether CRAP can help for optimizing the circuits?
So, well, VQE is supposed to be more general and to be able to deal with, even much more complex landscape in molecular dynamics and stuff like that. So VQE would be able to, of course, find the solution here much easier than our pedestrian classical algorithms. In fact, in a sense, if you wish, the results which Zoller with their variational ansatz achieved, he came to present them at the Gordon Conference on Quantum Control this summer, and he was really, acknowledging that this is a version of optimal control, if you wish. The very unique and amazing feature of what they have done there is that indeed, they, in their loop, there is a quantum circuit, not just a certain pulse, okay, a classical pulse, but there is really a full quantum circuit, and they optimize parameters in there. You can view this, if you wish, as a version of CRAB, but it is not. It is actually, of course, much more. But, I mean, it falls in the same category that I have a certain quantum dynamics which depends on a few parameters. Now, if I could use a full quantum computer implementation of VQE and apply to these landscapes, I could probably get better convergence and get there quickly. And now, we didn't propose that because, well, actually, yes, it could be an application, but I don't think there will be a huge market for quantum computers doing quantum optimal control, and our interest is really to have something which is practicable. In the future, this is something which is a very nice and good speculation. If one had a small quantum computer, one could use it to optimize this. And in a sense, a lot of the self-calibration, which, for instance, Google is doing and also IBM, is going a little bit in that direction, if you wish, in the sense that the quantum computer computes itself, okay, simulates itself, if you wish, and then you adjust. But then, if you look at things in this way, I mean, the boundary gets a little bit, of course, not so well defined. But the answer to, could I use VQE to get this minimization? Yes, yes, for sure.
Oh, but my question was actually a little bit the opposite, whether I can use CRAP to find the angles for the gates if I have some...
Oh, yes. Oh, yes. So, yes. That's actually, yes.
But is there already some interface on the cloud for your implementations to use it for some circuits to...
No, there is not. No, the interface that we have on the cloud is, until now, for sort of experiments. So for pulse shaping of time-dependent experiments. I mean, I should say that among the ideas that we are toying with for our startup, there is also that to offer this as sort of firmware for quantum computers in a sense. Okay, so like doing that.
Because with tensor networks, we often think of simulating VQE or something like this. But then we have to find the angles, and it would be nice to have also classical software that helps us quickly find the angles. so that we know what's ultimately the target circuits to even check and what is possible. And
Okay,
things like this.
so
Like,
that's okay.
so the classical benchmarking and classically trying to explore what could be a part of a NISC device has this ingredient that you have to find those angles. And then we have the rough landscape, and we can do convex optimization quickly, but as soon as it gets more difficult, then maybe CRAP could help.
Yes. Well, let's say that I think this is, we never thought in these terms, and this could really be, just theoretically, so to say, but not practically, this could really be a nice use case for our things. And maybe this is something that, actually, perhaps I should discuss this with Jens maybe next week when we are here at the workshop. That's actually a nice suggestion. Thank you for that.
Yeah, and I think some people from the companies are actually looking into things like this, that they simulate on the supercomputers, things like that.
Yes, yes. In fact, Atos is going to be here as well
Atos.
during the workshop, and probably this is also work that is related to that, yes. Thank you. So Simone also has a question.
Yes, thank you. Is there the possibility to use quantum optical control also for controlling the dynamics of a system and not just preparing a precise state?
Yes, but what would you mean in terms of controlling the dynamics?
For example, what is usually done in quantum simulation of gauge theories is to impose some huge energy penalty to the states that you want not to occur during the dynamics, but it of course has the limit. Is there some space for improving this sort of mechanism by using optimal?
I think so. I definitely think so, and certainly Simone Montangero, your boss, is one of the people who are best positioned to answer that question. I think that he had mentioned that he, in the future, in perspective, he might want to explore that. I'm not aware that he has done it yet, but yes, I am sure that it makes sense. How much improvement it can bring, because those are very, very complex simulations already, and this requires several iterations, so I do not know how feasible that is in the present state of the art. But yes, it is a perspective which certainly deserves to be taken into account.
Thank you.
It's fantastic. I mean, you give a talk, and every single person in the audience is asking a question. That's beautiful.
I have a little, let's say, more technical question, maybe, because I didn't understand well how do you choose the basis. So basically, the idea is that you have some random basis, and then you optimize over the coefficients somehow.
Yes.
But then how do you choose the
basis? That's a very important question. In fact, I have not said that. What I said is that often an initial guess can be taken at random, but that's an important tweak, so to say. So I hinted at that when I said that you choose the type of functions to which you know that your system is responding. Okay. Obviously, if you have an atomic system, okay, you are not going to send like a terahertz shaking of the trap, because this is not bringing anything. So somehow the time scale of the basis functions that you use must be within the time scales of typical response of your system. In this way, one can also say that using these methods, and there are ideas which, and actually Jens Eisert has been developing some of these ideas in terms of tomography, in which you are probing, okay, the system, you see which dynamics the system is responding to. This is a way to do spectroscopy, in a sense. Okay? And there are systematic ways to okay, so I really have to re-update my operating system, probably back to what it was. So it's in the reverse, it's also a way to probe which are the timescales on which the system is reacting. Spectroscopy, if you wish, is a simple and systematic way to do that. I just go in with a certain frequency and I see if the system does something, and then I change the frequency and so on. I see the reaction. So now, the more spectroscopic information you have about your system, the more you can incorporate in the choice of the basis. This is also, as we claim usually, this is a technical point, but it is an important one, an important improvement with respect to other methods such as genetic algorithms, which also work closed loop, but they are less efficient than this and require many more iterations, because with genetic algorithms, you take a certain pulse shape, then you break it down, you represent it in binary terms, and then you come to the next iteration by using genetic, like you mimic what nature does, like you do crossover mutation, like if this string of bits would be DNA strings, and then you generate the next generation, but you need many, many, many generations of that, like nature does, okay? And the reason is that that is like not incorporating any information about the physics. In our method, if you know that your system, is acting on a milliseconds time scale, you will work around that time scale, okay, already, because you know that it will bring something. And the random component in the frequency enables you sort of to drift also, not just to optimize the amplitudes, but also to allow the frequencies to adjust as you go on. So these are some of the important technical aspects, which then, of course, are implemented in this server that we have and that we offer as a service.
Okay, thanks.
Thank you.